When light is incident from a medium with larger index of refraction upon a medium with smaller index of refraction, depending on the angle of incidence, light can be completely reflected back into the first medium, and it will never go or enter the second medium. This phenomenon is known as total internal reflection. So let's look at the transition of light from glass into air. We know that the incident light ray is going to refract transitioning from glass into air. Since the index of refraction of glass is bigger than the index of refraction of air, the light will bend away from the normal. But if I keep increasing the angle of incidence, at some point I will reach a critical value known as critical angle, for which light will no longer pass from glass into air. So I am increasing the angle of incidence until it reaches a critical value, which is known as critical angle of incidence, and this value depends on the material from which the light is incident. And so once I reach that critical value, the light ray will no longer transition into the second medium. So it will refract parallel to the surface between the two, and then if the angle increases even more past the critical value, then the light will start to reflect back into the first medium. So when the incidence angle value is larger than the critical angle value for that material, essentially we are looking at a mirror effect. So the substance with the smaller index of refraction acts sort of like a mirror. And so when the angle of incidence is bigger than the critical angle, then we are talking about total internal reflection. So total internal reflection occurs when the angle of incidence is larger than the critical angle. Here's an example of total internal reflection. So in the first picture, we see laser light shone upon a glass piece which has a round interface with air, and then after that flat bottom. So the angle of incidence currently is less than the critical angle for the transition from glass to air, and we see that light gets refracted in air after it passes through the glass piece. And of course there is always some reflection here, which is just a result of the nature of the surface inside. There's always some reflection. Okay, but now the angle of incidence is increased, and now it is past the critical angle value for glass. And as you can see, all of the light is reflected back into the glass plate. No light passes into air. So this here is an example of total internal reflection. Right here. So what is the application of this effect or phenomenon in real life? Well, the most common application is transfer of information through optic fibers. So here's a piece of optic fiber that is not necessarily straight. It can have bends in it. And so I'm going to shine a light from a light source coming from the low open end, like this. So the light is carrying information, a signal, and the light rays are incident upon the optic fiber walls here at angles that are larger than the critical angle for transition from the material of the optic fiber into air. The material inside the optic fiber is silicon with some other additives, and obviously outside of the optic fiber we have air. So the index of refraction of silicon is larger than the index of refraction of air. So if the incident light is incident upon the interface between silicon and air at angles that are larger than the critical angle for transition into air, we are going to observe a total internal reflection. So the light rays will reflect and propagate inside the silicon or the optic fiber like so. Then they will reflect again, propagate like so. Then another reflection will occur like so. And again. And so on and so forth until the end of the fiber, where there is a receiver that will receive the signal and then transform it into zeros and ones. And then that would be either image or text or whatever the information was.